Hello! In this video, we're going to prove the following theorem. Let G be a group and suppose A is an element of G with order n. Then for all integers I and j, a to the power of I is equal to a to the power of j if and only if n divides I minus j. Now let's first remind ourselves what it means for a group element to have a finite order n. Given a group element A, to say that the order of A is equal to n means that n is the smallest positive integer such that a to the power of n is equal to the identity element of the group. Now, in proving this theorem, we are also going to be using the division algorithm, which tells us the following. Given integers a and b where b is greater than 0, then there exist integers q and r such that a is equal to bq plus r and 0 is less than or equal to r is less than b. And these integers q and r uniquely satisfy these statements. Okay, so now let's get into proving this theorem. To start the proof, let's first say that E is the identity element of our group G. And now we want to prove this statement. And since we're trying to prove a statement about every two integers, let's give ourselves two arbitrary integers. I'll call them I and j. From here, the whole goal is to show that this is true if and only if this is true. And to do that, we're going to prove if this is true, then this is true. And we're going to prove if this is true, then this is true. Let's start out by proving if this is true, then this is true. To do that, suppose a to the power of I is equal to a to the power of j. From here, we want to show that n divides I minus j. And a way that we can think about this is we want to show that when we divide I minus j by n, the remainder is 0. So we're going to apply the division algorithm to I minus j and n. So taking a to be I minus j and b to be n, then there exist integers q and r such that I minus j is equal to nq plus r and 0 is less than or equal to r is less than n. And the idea is to show that when we divide I minus j by n, the remainder is 0. So we want to show that r is equal to 0. Well, we know that r is greater than or equal to 0, so let's assume for a contradiction, we instead have that r is greater than 0. What goes wrong in this case? Well, the claim is that we can show that a to the power of r is equal to the identity element. But since n is the order of a, that means n is the smallest positive integer with this property. So that will imply n is less than or equal to r, which contradicts the fact that r is less than n. So, to see how a to the power of r is the identity element, we'll notice we're going to take a to the power of r and multiply it by the identity element. But, in fact, the identity element to the power of any integer is equal to the identity element. So we can replace e with e to the power of q, and we know that a to the power of n is equal to the identity element, so we can replace e with a to the power of n, so we get this. But then, by properties of exponentiation, a to the power of n to the power of q is equal to a to the power of n times q, because we can just multiply the exponents. But then, by properties of exponentiation again, here we can just add the exponents. So we get a to the power of nq plus r. But we know that nq plus r is equal to I minus j. So this is just a to the power of I minus j, and by properties of exponentiation again, this is a to the power of I times a to the power of negative j, and we know that a to the power of I is equal to a to the power of j. So we can replace a to the power of I with a to the power of j, so we get this, but then we can just add the exponents. So this is just a to the power of 0, but then, by definition of exponentiation of group elements, a to the power of 0 is the identity element. So this shows that a to the power of r is equal to the identity element. But remember, since the order of a is equal to n, we know that n is the smallest positive integer that has this property. So n must be less than or equal to r. But this contradicts the fact that r is less than n. our assumption that r is greater than 0 led us to a contradiction. So we must instead have r is not greater than 0. Now we know that r is greater than or equal to 0, but we've just eliminated the possibility that r is greater than 0, so we must have r is equal to 0. And now that we know r is equal to 0, this tells us I minus j is equal to nq plus 0, or in other words, I minus j is equal to nq. And so we see that I minus j is equal to n times some integer. So n divides I minus j. And that is exactly what we wanted to show. So we have shown if this is true, then this is true. Now let's show the other direction. We're going to show if this is true, then this is true. To do that, suppose n divides I minus j. From here, we want to show that a to the power of I is equal to a to the power of j. Now since n divides I minus j, this means that I minus j is equal to n times some integer. I'll call the integer k. And now we're going to show that a to the power of I is equal to a to the power of j through a chain of equalities. First, we can re-express I as I minus j plus j. And then, by properties of exponentiation, we can re-express this as a to the power of I minus j times a to the power of j. But then, we know that I minus j is equal to nk. So we can replace a to the power of I minus j with a to the power of nk. But by properties of exponentiation again, a to the power of nk can be re-expressed as a to the power of n to the power of k. But then, since the order of a is equal to n, we know that a to the power of n is the identity element. So we can replace a to the power of n with the identity element. But then, we know that the identity element to the power of any integer is the identity element. So this is just the identity element times a to the power of j, but then, by definition of the identity element, we know that this is just a to the power of j. And so we have shown a to the power of I is equal to a to the power of j. And that is exactly what we wanted. So we have proven if this is true, then this is true. And at this point, we have proven both directions of this statement. And we have proven this statement for two arbitrary integers I and j. Since I and j were arbitrary, this means we have proven for all integers I and j, this is true. And that is exactly what we wanted to prove. So this completes the proof. Now, a corollary of this theorem is the following. Let G be a group with identity element E, and suppose A is an element of G with finite order. Then, for all integers k, a to the power of k is equal to the identity element if and only if the order of A divides k. And to see how this can be proven, well, since we're trying to prove a statement about every integer, let's give ourselves an arbitrary integer. I'll call it k. And now, we want to prove that a to the power of k is equal to the identity element if and only if the order of A divides k. And to do so, we can apply the theorem that we just proved. So applying the theorem, well, since our element has finite order, we're going to take n to be the order of A. We're going to take I to be k. We're going to take j to be 0. Well, then in that case, we have a to the power of k is equal to a to the power of 0 if and only if the order of A divides k minus 0. But since k minus 0 is equal to k, this statement is equivalent to saying order of A divides k. And we know that a to the power of 0 is equal to the identity element, so this is equivalent to saying a to the power of k is equal to the identity element. So, through this chain of if and only ifs, we say that a to the power of k is equal to the identity element if and only if the order of A divides k, which is exactly what we wanted. So this proves the corollary. And so yeah, that's pretty much it for this video.